Okay, hello guys, it's Orish. Today in our new video we are going to complete the drawing. We are going to do a bit of structural analysis and we are going to complete the drawing of the bending moment and the shear force diagram of the previous exercise, if you remember in the last video. So okay, in the last video we had a simple supported beam, statically determined structure. We analyze the structure. What is analyzed? Analyze the structure and to evaluate the structure, to evaluate the behavior of the structure in response to a load that is applied on it. Okay, so we started analyzing our structure the last time. We did not draw the bending moment, so we will draw the bending moment of this structure. This is the shear force that we got the last time. Shear force was equal to 1 kilonewton. The bending moment was equal to x kilonewton meter. Okay, so how do we draw the shear force diagram and the bending moment diagram? You can use a table for the case of a concentrated load. You can use a small table like this, where you put a certain number, a certain number of information. Here you can say forces, for example. Okay, here you can say you have because apart from the force, you have the point, let's say point A. Okay, so as I said, here we have the first column will be for the force. The forces. Here the point A, here point B, not point B but point C instead. Point C. This is x corresponding to 1.5 meters. Our column in the case of the concentrated load will have only our table in the case of concentrated load will have only 2 points to be used to draw the diagram. So here will be the point x equal to 0. Okay, here we have the shear force, which is equal to 1. Okay, it means, and let me represent point A here. This was our point A, this was point B, and the point C that I just named now will be this point at the center where the load is applied. So this is the bending moment. We got x as the bending moment. Okay. So you draw just a small table like this. When you are done analyzing your structure, as the table is drawn, you see the shear force is already constant, so you just have one there. At x equal to 0, you have 1 r. X equal to 1.5, you have 1x also. Here x is ending at 1.5 because we make one section in between A, from A to a certain distance x, which where we consider x to be in between 0 and 1 and 1.5. That's in between 0 and the load, because the load is applied at the center of our structure, which is at exactly 1.5, since the length of our structure here was 3 meters. Okay, so remember this is the case of the concentrated load. Why are we ending here at 1.5? Because at the other end of the structure, we just have to repeat the behavior of the structure at the other on the other side by just making it to go opposite to the first side where we make a cut, because the behavior of our structure will be the same on the both sides, just be of negative opposite direction. Let's say opposite direction. Okay, so here we have the bending moment equation, which Bm is equal to x. At x equal to 0, we have 0. At x equal to 1.5, you have 1.5. Okay. At x equal to 1.5, you have 1.5. At x equal to 0, we have 0. Okay, we have 0 at x equal. So now we are going to draw our bending moment diagram. And our shear force diagram. It will not be that accurate, but The objective here is just for you to understand the principle or the methodology. Okay, so let's say that this is the first. This line is representing our structure that we have projected. This dotted line represent localize the center. Okay, we will start by the shear force diagram, and then we will draw the next diagram will be the bending moment diagram. Okay, for the shear force diagram, you can see that the shear force diagram here is constant. At x equal to 0, we are here. At x equal to 0, we are at 1. That's, let's consider from here, from this projection of our structure to a certain height here, let's consider this to be our 1. Okay, this 1. Okay, at x equal to 1.5, which is the middle of our structure, we are still at 1. So let's project. Let's draw a line to join the 2 points because we have a point here. So at x equal to 0, we are at 1. At x equal to 1.5, we are still at 1. As I said, for the case of a concentrated load, no need to make like maybe 2 sections because 2 cuts, because there are structure where it will be obligated to make maybe, let's say 2 cuts or 3 cuts, even more, depending on how the structure it is. But here we have a simple supported beam with a concentrated load applied. It means the behavior of the structure in this side where we make our cut will be the same here, but of opposite direction. What do I mean by opposite direction? Here we have the shear force diagram already. You have the shear force diagram on this side already. If we say of opposite direction and from the same of the same property, let's say the same magnitude, it means we will still have, but here on this side we will have -1 and then -1 exactly also here. Okay, so this will be our shear force diagram. This will be our shear force diagram. This will be 1, this will be 1 here, and this will be 1, 2 here. Okay, so that's how we are going to represent our shear force diagram. Let's abbreviate it to the SFD. Okay, so as I said, if we make a cut from here, from point B to the center here, we still consider the point B to be our 0, and in this case, if we analyze it, you will see that if we consider we make a cut from B, for example, from B to the load, we will see analyze it the same way we analyze it from A to the center. But in this case, we will not more have but 1 has the shear force, but we will have -1 has the shear force. If you are to analyze it, you will see that you can check it, make the cut and analyze it following how we analyzed in the previous video, and you will see that you have but -1 like the shear force. That's why we say for a simple supported beam with a concentrated load, we don't need to make 2 cuts because the behavior of the structure, which is this beam, will be the same on the both sides, just that the other side will be the opposite of the other one in terms of magnitude, remember. Okay, so now let's draw the bending moment diagram. Okay, let's take it like this. Okay, let's take it like this. Let's consider this point to be the center. Okay, at 0, this is the equation of the bending moment. Bm is equal to x. At 0, at point A equal to 0, which is our point A here, you have 0 as bending moment, which is normal because you have a hinge support here. There is no moment at the hinge support and roller support. There is no moment at those support. So if you by analyzing your structure, you find maybe a moment here at the hinge support or at the roller support, it means something is wrong in your manipulation. So normally we are supposed to have exactly this 0 at A, which is the hinge support. We are supposed to have bending moment is equal to 0. So we have 0, it means we are down here. Okay, and at x equal to 1.5, at x equal to 1.5, you have 1.5. Okay, so we will consider our 1.5 to be somewhere at this position. Then we will project it to the center here. Let's say that this is our, the drawing would not be that accurate, but it's just for you to understand how we proceed, the procedure. Okay, so this is our 1.5. Let's say that this is our 1.5. Then now we'll join the 2 points. At x equal to 0 we are here, at x equal to 1.5 we are here, so you just join the 2 points. Okay, and as I said, it's a concentrated, simple supported beam with a concentrated load. So the behavior of the structure on this side will be the same here, but just of negative sign. That's the implication, and it's normal because at the end we can notice that we have a roller support on the other side. So let's just draw. So this will be our bending moment diagram. Let me remove the dotted line. Okay, so here we have 0. Sorry, the marker is a bit disturbing. 0, and here we have 0, and here we have 1.5. Okay, so here we have 0, here we have 0 as bending moment, and here we have 1.5. Remember, this value are the value of the bending moment at those different positions. Same as here we have 1, here we have -1. Since we are down on the negative part here, no need to put the negative in front of 1 because we are already downward. So that's how the bending moment and the shear force diagram and the bending moment diagram looks like for the simple supported beam with a concentrated load applied on it. I hope you got the principle. For a hinge support or a ruler support, which is hinge support and ruler support, always remember you should always have 0 here at the bending moment, 0 and 0 on the other side. It's only for the fixed support that you have a bending moment or a moment at those support. Okay, so this is the diagram of the bending moment and the shear force for our previous side. Thank you. If you like the video, you leave me a like, and if you have a question, leave it in the section comment, activate the notification bell, and let's follow for the next video. Thank you.